So today we are very happy to have Tanja Hinderer visiting from University of Maryland, and she's going to tell us about gravitational waves.
Okay, thank you all for coming. So roughly the plan for the talk is that I'll first give you some general background about gravitational waves, which you might have heard of a lot recently.
Possibly, maybe.
Yeah. And then I'll focus mainly on the waves emitted by binaries, for which it's really important to have accurate theoretical models of the expected signals to be able to extract all the information contained from the waves. And I'll give you some idea of recent progress we've made on constructing such models. So I'll first discuss spin effects for black hole binaries, and then tidal effects in neutron star binaries, which would tell us about the properties of the dense matter in their interior. And then I'll mention some very interesting features in highly relativistic binaries. So one of the main motivations for gravitational waves comes from considering some very interesting objects in the universe. So the first class of objects is seen in the centers of many galaxies, including the Milky Way, where, for example, orbits of stars near the galactic center indicate that they are orbiting around an object over 4 million times the mass of the Sun, but concentrated in a very small region. And that might be a black hole. And the other interesting class of object is seen in the debris from the death of a massive star that exploded in a supernova explosion. And here you see an example, what is now the Crab Nebula. It's from a supernova in the year 1054. And from its central region comes an intense emission of high energy radiation, which turns out to be produced by an object with mass just a bit larger than the mass of the Sun, but rotating at 30 revolutions per second. So it means it must have an extremely small radius, otherwise the material would be flung away very quickly, and that's a neutron star. And you can see that from these electromagnetic observations, they tell us that those are very bizarre objects, but they don't really allow us to probe the detailed properties of the objects themselves. But to do that, we can now use a different type of radiation, which is gravitational waves. And these waves now allow us to see things like the mergers of two black holes, like you heard the recent news, which we cannot otherwise see. So before discussing gravitational waves, let me just remind you about the nature of gravity according to Einstein. So he postulated that space and time themselves are dynamical entities that curve around matter and energy. And that curvature is responsible for gravity in the sense that then everything moves on the straightest possible path in the curved geometry. And this has been measured to high accuracy in the solar system. For example, here you see a cartoon illustration of such a measurement, where this is supposed to illustrate an equatorial slice through the Sun, and then the third dimension is supposed to give you a sense of the curvature. And for example, here a measurement was the delay in radio signals passing between Earth and the Cassini spacecraft, and since the ray has to travel in the curved geometry, it takes longer than it would in the absence of curvature. And the curvature of time is used every day in the global positioning system, where the GPS satellites orbit at around 20,000 kilometers above the Earth. And the Earth curves time in the sense that time flows slower for us on Earth than it does at the altitudes of these satellites by about 2 parts in 10 to the 10, so a very small effect, but it accumulates and over a day would lead to positioning errors of 5 kilometers. And so since space and time behave very similarly, Einstein considered them as parts of a unified entity he called space-time. So another interesting prediction of Einstein's relativity is the following. So I showed you before the cartoon of the curvature produced by the Sun, which is pretty small. But if the Sun were compressed to a smaller radius, it would produce a much larger curvature. And under even further compression, eventually the curvature becomes so large that the matter collapses on itself and disappears from the view of the outside universe. And that forms a black hole. So a black hole is essentially a region of intense space-time curvature. It has no surface, just an event horizon, which separates information in its interior from the outside universe. And the interesting feature of black holes is that it is entirely described by 2 parameters, its mass and its spin, which is unlike objects like the Sun, for which you also have to specify the composition and shape and radius and so on. And when a black hole is rotating, it even drags space around it into a whirling motion. And a black hole also has a maximum spin limit, which occurs when its event horizon is rotating at the speed of light. Okay, so this is distortions in the space produced by stationary objects. But now you can imagine when objects are accelerating, they will produce time-dependent deformations in the curvature, and those ripples in curvature will travel away at the speed of light, and those are the gravitational waves. And they are typically characterized by a dimensionless amplitude h, which gives sort of the fractional deviation away from flat space. And that amplitude scales like a combination of fundamental constants, which is an extremely small number, and then the second time derivative of the quadrupole moment, or moment of inertia of the source, and they fall off like 1 over the distance to the source. So to overcome this small prefactor of fundamental constants requires having large masses moving at highly relativistic speeds to get any kind of appreciable amplitude, and those would only be astrophysical sources. And by the time the amplitude reaches the Earth, they're still only of order 10 to the minus 22. So we don't notice these waves in everyday life. But to create such a tiny amplitude requires an enormous amount of power. So in this case, for the number above, it's 10 to the 51 watts. So that means that in a sense, space is like a very stiff medium. So it requires a huge amount of power to create just a tiny vibration in it.
So the mass up there, is that the combined mass or some mean mass for the two inspiral objects?
That is the combined mass, but it's assuming they have equal masses.
Mm-hmm.
So it's not the full dependence on the masses shown
so
there.
This equation was definitely for the time when people thought neutrons are neutron stars.
Exactly. Exactly. Yeah.
I think they Photoshop perhaps the black into the white.
Could be. Yes. Yes. Yeah, so a key feature of gravitational waves is that they interact very weakly with matter. So they pass through any gas and dust without any scattering or absorption. So they propagate nearly uncontaminated. And besides two objects orbiting one another, there are many other mechanisms to produce gravitational waves. There are many processes in the early universe that could produce them: supernova explosions, mountains on pulsars, and many other things. But I'm just going to focus on the binaries here. So the effect of gravitational waves on the source was already observed before LIGO made the detection from binary pulsar measurements. So a pulsar is a rotating neutron star that emits a beam of radiation, and then when the beam crosses the field of view of the telescope, it looks like there's a pulse of radiation. And these pulses occur at very regular intervals, so from timing them one can infer details about the system itself. So this most famous pulsar was the Half-Taylor pulsar discovered in 1974, and it's in orbit with the normal neutron star companion. And we expect, from the orbital motion that should generate gravitational waves, and they carry away energy and angular momentum from the source. So we expect the orbit to shrink and therefore the period to decrease. And that's precisely what was observed in the data. You see here the plot, the cumulative change in the orbital period relative to the value when it was first observed over the years. And the data points agree very well with the prediction assuming gravitational wave emission. And so at the time, this was actually it had a huge impact on the field, because prior to those measurements, it wasn't clear at all if gravitational waves are actually physical, and second, if they actually transport energy. And because at the time, different calculations gave completely different results, and people were very skeptical about that gravitational waves really exist. So that these measurements really helped to advance the field. So now we consider the waves once they've propagated far away from the source and might reach a distant observer. So these waves are transverse, so they cause distortions in space perpendicular to their direction of propagation. And these distortions are an oscillatory stretching and squeezing of space along orthogonal axes. And they occur in such a way that the relative length between 2 points changes, and the fractional change in length is directly proportional to the wave amplitude. So that tells us if we want to measure the waves, we have to look for changes in length. And a convenient way to measure these changes in length is with an interferometer. So a very basic principle is illustrated here. A laser travels through a beam splitter, gets divided into 2 perpendicular beams. They travel down each arm, get reflected off the mirrors, recombine, and then the interference pattern is read out at the photodiode. So then as a wave passes, the arm lengths will change in different ways. So the relative round trip time in the arm changes. So when the beams recombine, they have a difference in phase. And that translates to a difference in intensity that is measured at the photodiode. So this provides then a direct measure of the gravitational wave amplitude. And that's sort of very oversimplified, of course, the principle behind LIGO, the Laser Interferometer Gravitational Wave Observatory. And these are gigantic instruments with 4-kilometer long arms and 40 kilogram mirrors, everything under ultra-high vacuum, high-power lasers, and they've become so sensitive now that they can measure changes in length of order 10 to the minus 18 meters. So that's really an incredible sensitivity. But this sensitivity can only be achieved in a certain range of frequencies. So in terms of the binary inspirals, that translates to binaries that have orbital periods of order 100 milliseconds or less. And that's only a small fraction of all binaries will have that short of an orbital period. So here again is a plot that came from the case when people considered the binary neutron stars. To give you a sense of the relative improvement, one considers the visible volume of the universe to LIGO to these binary neutron star inspirals. So when initial LIGO started out in 2001, it could see these inspirals only in our own galaxy. And then by 2010, it had already increased its visible volume by a lot. And then came the upgrade to Advanced LIGO, which gave a factor of almost 10 improvement in the visible volume. And now over the next few years, it will continue to increase in sensitivity and increase the volume about by a factor of 30 or so. So of course, that's just a reference. The black hole binaries with larger masses can be seen out to much further distances. So that there's a much larger volume of the universe visible. So LIGO is in fact part of a worldwide network of similar detectors. It's currently the only operational one, but there's Advanced Virgo in Italy, which has almost completed its hardware upgrade and will hopefully soon come online. There's a smaller detector, Geo 600 in Germany, and Kagra in Japan is under construction, should become operational in 2020. And then just last week, LIGO India got approved, so construction can begin also there. And there are also plans to have a detector in space called ELISA, Evolved Laser Interferometer Space Antenna, which would be launched in 2030 something. But for that, a technology Pathfinder mission to test all the required technology was launched last December. So now I want to consider in more detail the gravitational wave signal itself from these binaries. So here you see from two black hole binaries, which are similar to the setup of LIGO's first detection. And the map is just to give you a sense of the scale involved in these systems. So as the objects orbit one another, they generate sinusoidal gravitational waves, and the orbit shrinks. The objects move faster. They reach almost half the speed of light. And at the same time, the frequency and amplitude of the waves increases until the objects become so close that they collide, which creates a large disturbance in the space-time and coincides roughly with the peak in amplitude. And then they merge into a single black hole, which is initially highly perturbed, and then it rings down to a stationary state. And in fact, the detailed shape of these waveforms contains a lot of information about the parameters of this binary. So you see an example of equal mass, no spins. A waveform for unequal masses already looks more asymmetrical. And then when the objects are spinning and the spins are not aligned with the orbital angular momentum, there are some characteristic modulations in the waveform. So to extract all this information from the observed signals requires having some models of the dependence of the signals on the parameters. And these models are then used to build a bank of templates or theoretical waveforms for all possible source parameters. And this template bank is then cross-correlated with the data to make the measurements. So it's quite a challenge to compute such accurate templates because it requires solving the two-body problem in general relativity, which is very difficult. So we have to solve for the dynamical space-time geometry describing the binary, where the sources are not just the mass density like in Newtonian gravity, but also the pressure, the flow of energy, flow of momentum, and so on. So in the end, one ends up with 6 coupled highly nonlinear differential equations in 6 variables. And also the equations of motion are much more difficult. So to tackle this problem, there are different approaches in different regimes of the parameter space. So here you see the parameter space in terms of the orbital separation and the mass ratio. So at infinite orbital separation, we have Newtonian dynamics. And as you go down in this plot, the system gets more and more relativistic. So starting from Newtonian dynamics, one can systematically compute relativistic corrections, and that's known as post-Newtonian theory. And this is very successful for the solar system and even for the binary pulsars, but eventually it breaks down. But there is a way to analytically access the strong field regime, which is in the test particle limit, in the infinite mass ratio limit. So there is a test particle which produces no space-time curvature of its own, orbiting a much larger object. And then again, one can start from that limit and systematically include mass ratio dependent corrections, doing black hole perturbation theory to extend in the parameter space. But then for comparable masses at small separation, there's no analytical approximation method, and we have to use numerical relativity, which involves solving Einstein's equations on supercomputers. And these simulations are extremely computationally expensive, so it takes several weeks to months to do just one case with a few orbits. So simply by computational costs, this method is limited to this small corner of the parameter space. But now, during an inspiral, a binary moves, of course, from large separation to small separation, and LIGO's frequency band is such that it sees the more comparable mass regimes. It doesn't see these very unequal mass binaries. And you see the problem here. For data analysis, we need complete waveforms that describe the entire path to merger. But first of all, there is a gap between the post-Newtonian description and numerical relativity, and also it's not feasible to do 250,000, which is the number of templates needed for LIGO, numerical relativity simulations. So we have to come up with something that can be used for the data analysis. And one method that can be used is a so-called effective one-body approach, or EOB model. And there, the idea is similar to what one would do in Newtonian gravity, where instead of solving the two-body problem as such, one simply solves for the motion of the reduced mass in the field of the total mass. And this effective one-body model is sort of a relativistic analog of that, where one has an effective particle with mass, the reduced mass, and it could also have an effective spin, and it's moving in a space-time characterized by the total mass and the total spin. And this setup is such that in the test particle limit, this reduces exactly to the motion of a test particle in the black hole space-time. But then there are mass ratio dependent corrections to the space-time itself, chosen in such a way that it reproduces the post-Newtonian limit. And this model has 3 parts to it. It has a Hamiltonian for the conservative dynamics, some radiation reaction forces, and a prescription for computing gravitational waves. And you can also ask questions during the talk if you want, because maybe you haven't heard about this effective one-body. Okay. Yeah. So to test this model and see if this kind of ad hoc approach is actually a good approximation, we first, before testing the gravitational waves, we also want to test the underlying dynamics.
So actually I have a question for the spin. So
yeah.
At the end you have 3 aspects. So you have the spin of the 2 objects, and
yeah.
then how they align compared to the orbital motion.
Yeah.
So how can you compare or translate or map that onto this effective one-body model?
Yes, so this effective spin of so the total spin of the space-time is the magnitude of the spins, the sum of the spins, but this effective spin is actually not a spin. It's only a spin in the test particle limit, but otherwise it's just a function of all the variables in the system. So then it's a function of the two-body spins and of the orbital momenta and so on.
So how can you decompose afterwards? Because if I remember correctly from the gravitational wave results, they did have constraints on the spins of the 2 objects.
Yeah.
But then there were differences for the spin that's parallel to is it how the orbitals spin versus perpendicular? And so there are different constraints for that. So that was, that's the next steps that are very interesting to see, why you have these two black holes in this binary in the first place. I mean, there's lots of discussions about that. So I'm just hard for me to see right now from this effective one-body model how you can decompose that back.
Yeah, so actually, if you're talking about the waveform, the way it's done in this effective one-body model is we first get a waveform for the case of aligned spins, because that gives all the secular spin effects that modify the interaction between the bodies. And then we simply apply a geometric transformation that is just a time-dependent rotation to get the processing waveform.
So am I about this? So am I supposed to think about this model as kind of phenological model, or there is a really consistent expansion scheme such that I can improve?
No, it's just a way to combine the perturbative expansions in terms of the mass ratio and in terms of the post-Newtonian, just to interpolate between the two.
But is there a control of kind of theoretical uncertainty when I really go in the regime when it becomes not like numerical relativities?
Yeah.
So is there control of error which one is making?
Yes, so it can be assessed by simply comparing the predictions of the model to numerical relativity. Yeah, and I will say a little bit more later about this also. Yeah.
What about the ring down? Is the shape of the wave function known relatively?
Yeah, so the ring down can be computed perturbatively simply by considering a single perturbed black hole. It has some quasi-normal modes of oscillation, so some like resonance frequencies. So that is analytical.
Is this separate from this approach?
Okay. No, the idea is to use this approach for the inspiral, and then in this model there is a certain feature that tells you that the end of the inspiral is reached, and then at that point one attaches the ring down, so to say, yeah. There's a small transition window, and then comes the ring down.
And ring down you can do analytically, you can fit late stages, right?
Yeah.
Okay.
Yeah. Okay, so to test this EOB dynamics first, before considering the gravitational waves, we want to compare with numerical relativity. And so we have to pick some quantities that are gauge invariant and can be computed in both approaches. So one such quantity is the periastron advance, which is famous in the solar system as the perihelion advance for Mercury. And the effect is illustrated there. So Mercury's orbit, due to various perturbations from other planets and non-spherical shape of the Sun, and also due to relativity, is not a perfect ellipse. Instead, the time taken to make one revolution, which is the blue dashed line, is shorter than the time taken to get back to the same radius, which is between the two red dots. So in between a phase delta phi accumulates, which is the periastron advance. And now we don't want to consider Sun and Mercury. Instead, we have two black holes with aligned spins, and we compute this effect for that configuration. And in the EOB model, that can be derived from the Hamiltonian and then compared to numerical relativity. And you see the result illustrated down here. You see the periastron advance per orbit, which is about 90 degrees, and the orbital velocity, which is still far from the merger. And the blue shaded region is numerical relativity, which has some uncertainty in it, so it's a range of values. And you clearly see the pure post-Newtonian is not consistent with numerical relativity, but instead repackaging that information in the EOB model works pretty well, at least for the configurations we could test. And this is a case for almost maximal spins on the black holes. So now to the EOB waveforms. So we recently improved the modeling of spin effects in these waveforms too. And then we found that, as we discussed, the waveforms work pretty well, but they don't really capture the near merger part very nicely, because if you have just analytical perturbative information, maybe it doesn't reproduce exactly the strong field behavior. But instead, what we do is we include a few free parameters in the model to, yes, a question? Okay. A few free parameters in the model, which we fix by comparing with numerical relativity simulations. And then once these parameters are fixed, the model is supposed to work very well over a large range in parameter space. And you see here the result of a waveform comparison over 50 gravitational wave cycle. The model seems to work very well once we calibrated these coefficients. And in fact, this was one of the two models that was used in the data analysis of the event. And as I said, for non-aligned spins, we simply take this waveform and then apply a time-dependent rotation to get the precessional effect.
And how PPN would look on the same plot? It would be completely off already?
Yeah, PN would be, well, PN already doesn't have the merger and ring down part. So it would work maybe up to here or so, I don't know exactly, but it would start to build up a dephasing. Okay, so for black holes, as I told you, they have only masses and spins. So of course there's a lot more work to be done on these models, but we have some basic understanding of possible features in the waveform. So now things get even more interesting when neutron stars are involved, because then we have also all the physics of the matter coming in. So just
are you going to say a little bit more about what these parameters mean? You mentioned
the calibration parameters?
Yeah. What is is there a physical?
So we have one parameter that sets sort of the horizon of this effective space-time to some value. We have one parameter for the spin effects, a spin-spin interaction and a spin-orbit interaction. And then there's a parameter to control the transition between inspiral and ring down. Those are the basic parameters.
So was your work then DUB approximation used to make these templates and
Yes.
the database that they then used to search for the gravitational wave signal?
Yeah. So they used this EOB model, and then they used another model, which is sort of a phenomenological frequency domain model, just to be sure, there aren't any systematics in the models that spoil the measurements.
29 divided by 36 is not such a small number. So you said the model had expansion in power, so the ratio of the masses. Or maybe I misheard that.
This EOB model is supposed to be a non-perturbative resummation of all these perturbative expansions.
So how do you resum those?
Well, in an arbitrary way. For example, we write Taylor expansion. So, the first thing is we resum so that it looks like a particle moving in an effective space-time. That's the first constraint. So then we change the metric potentials of that effective space-time. We just include some corrections to them. And there we, instead of, for example, since we have the other constraint, we have to reproduce the post-Newtonian results. Instead of putting a Taylor expansion in the potentials of post-Newtonian-like terms, we write, for example, a logarithm of that quantity, that post-Newtonian result.
I guess this goes back to what Sergey was asking. Is there a systematic way of doing those things, or it's like adjustment as you go? In terms of,
so
if I sit down and have a piece of paper, can I have an algorithm, systematic algorithm, what I should be expanding?
Yes, up to arbitrary choices like rewriting things as logs in terms of instead of Taylor expansions. But otherwise, yes, you have say for non-spinning, you start from a Schwarzschild space-time,
Yes.
and then you by hand modify the metric potentials. You add some mass ratio dependent corrections. And it turns out that you add one coefficient to these potentials, 1 minus 2m over r, and then plus one more coefficient. And that already reproduces all the PN results to 1 PN. And the PN is quite long and complicated, but it turns out in that model, you just need one coefficient to reproduce that result.
I guess the answer to your question would be no, right? There is no systematic expansion which allows to approximate the exact solution with the arbitrary precision, but you don't need it for practical purposes, I understand, right? So it's really kind of phenomenological model which within current accuracy which is needed, derivation does the job.
It's not a solution to...
There is a second part to the question as well, which is that whether in principle it's an expansion around something that's a numerical GR gives you, or exact solution gives you.
Yeah.
Is it?
Well, say it's not a solution to Einstein's equations in general, but it is a solution in the test particle limit and in the post-Newtonian limit. And in between, it just smoothly interpolates somehow.
So, very good. If those expansions really become asymptotic and diverge in that limit, there is no guarantee that expansion really will produce that solution.
Right.
Because there is no parameter there, right?
Looks
So,
like, yeah.
Yeah.
Right, because in the plane that you had, you had post-Newtonian approximation here, you had the space-time black hole perturbation theory. You want basically it's a way of merging these two and going the diagonal to the lower left, right?
Yeah. And then to fix some coefficients using information from numerical relativity.
It's a way of merging these two and going.
That's just a fact of life. There is no parameter there to expand, right? So you just trying to do something phenomenological.
Yeah.
And what is the ultimate accuracy goal which you need for from observational point of view for these waveforms now and in the future perhaps?
So that depends on the signal to noise ratio. So at the moment, this model was good enough to do the parameter estimation, but in the future it has to be improved and also extended in larger regions of the parameter space.
So the nice kind of, just to follow, so I mean, when we saw, last week, the very beautiful results and how actually the models, very consistent with the data. So in terms of those models, were they part of the library bank? Or was it such once the generic algorithm found the signal, then you or your colleagues reran kind of your models or something to make it really fit nicely to the data?
No, I mean we don't fit the models after we get the data. They're contained in the bank of templates, but then for parameter estimation they go really in more. They have a much finer template bank, and they also, because the waveform was so short, it was only 10 cycles. It was possible to run after it was clear sort of what the parameters are of this system, roughly estimated from these models. They could run some numerical relativity simulations to make sure actually these models are good and everything is consistent.
Has it been done for those parameters which were observed or not?
Yes. So immediately after that was observed, the numerical relativity, they all started simulations, which took several months, but it finished before the analysis was finished, so they could use them and verify that everything is consistent.
And the fact that one is 29 and 136 versus 30 and 35 is which model confirmed that? The numerical GR or your type of?
All of them.
All of them.
Yeah, but all these masses, they're just approximate. I mean, there's still an uncertainty in these masses.
What's the uncertainty?
I don't remember exactly, maybe plus or minus 5,
Plus
but I don't know exactly.
Okay.
Yeah, you remember? Yeah.
Was it plus minus 4? Plus minus 4. Okay.
Plus minus 4. Okay. So any more questions about this effective one-body and black hole waveforms? Okay, so now let's get on to neutron stars. So just to remind you, these are the densest objects in the universe, and they have masses a bit larger than the mass of the sun, but all concentrated to a region with radius maybe 10 kilometers. So matter in the interior gets up to several times the density of an atomic nucleus. And at that point, our understanding of nuclear and fundamental physics completely breaks down. So a long-standing question has been to determine the properties of this dense matter. So now I want to tell you, what we can learn from gravitational waves. So here you see two waveforms. One is neutron star black hole, and the other one in black is the double black hole that we saw before. And if we start from the left, so when the objects are far apart, they behave essentially like point particles, no matter what kinds of objects they are. So the waveforms are identical. But then as the objects approach and we get closer to the right in this plot, you see there's a small dephasing between the waveforms building up, and that's due to tidal effects, where the neutron star deforms because there's now a differential in the gravity across its mass distribution. And to leading order, this deformation, which I call QNS here, is proportional to the tidal field. If you put a larger tidal field, it deforms more. And the constant of proportionality is its tidal deformability. sometimes you see an analogous expression, you have an induced dipole proportional to the electric field, and then it's the polarizability that comes in. So since neutron stars are strongly gravitating objects, this coefficient has to be calculated from Einstein's equations, but that can be done, and one can take one's favorite model of neutron star interiors and see how this parameter looks in terms of the neutron star mass. And that's illustrated here, where the tidal deformability is in some convenient units, and then on the x-axis is the neutron star mass. So you see for different models, having normal nuclear matter, which is the blue curves, or with hyperons, which are some particles that appear at high densities, and then in orange is strange quark matter. So you see there's quite a range in values, and it would be best to measure this parameter for several masses to really map out one of these curves. So how does that now influence the gravitational waves? So first of all, some energy is associated with deforming the neutron star, so that changes the total energy of the system. Second, these moving tidal bulges contribute an extra bit to the gravitational radiation, so it changes the energy loss of the system. And then one can compute the gravitational wave phase as follows. One says, well, the dominant wave emission occurs at twice the orbital frequency, and the orbital frequency evolves according to the balance between the loss of energy to gravitational waves equals the change in energy of the system. And then one can go through and calculate what is the tidal contribution, and one finds that it's proportional to the tidal deformability parameter. It also scales like the velocity to the 10th power, so it indicates it's only important at the very end of the inspiral. And it also falls off as 1 over the total mass to the 5th power. So when the black hole becomes very massive, this effect also goes away. And we also then calculated post-Newtonian corrections to this to extend the validity of this model. And recently, we further improved the modeling of matter effects by taking into account an additional effect, which is the following. So in fact, this induced quadrupole corresponds to the fundamental modes of oscillation of the neutron star. So the neutron star is sort of a ball of fluid, so it has many normal modes of oscillation, and the quadrupole happens to be one of those modes, or one class of those modes. And their frequency is pretty high, typically higher than the tidal forcing frequency that is reached during the inspiral. But towards the end of the inspiral, the two can become roughly comparable, and there's an enhanced response of the neutron star, similar to a harmonic oscillator that is driven almost near its resonance. You see this here. I plot some quantity related to the neutron star response versus the ratio of tidal forcing to resonance frequency. And you see the constant tidal deformability value is okay at low, but let's say early on during the inspiral, but then towards the end of the inspiral, it becomes important that there's a frequency-dependent enhancement. And typically the inspiral ends before the full resonance is reached, but maybe not always. It requires further exploration. So we've then included these effects also in this effective one-body model, and then we can now compare again with numerical relativity results. And for this comparison, I'm just going to show you the very end of the inspiral, the last 4 gravitational wave cycles. And instead of showing the waveforms, I'll just show you the phase difference between the numerical result and the models. So this you see here. And again, the numerical relativity is a gray shaded region because it has some error associated with it, because it's also for numerical relativity quite difficult to have high accuracy simulations involving neutron star matter. And the blue line here, the black line here, is the double black hole result, which is essentially 2-point particles. So that line gives you an estimate of the net size of all the matter effects. And you see the adiabatic tidal model captures most of these effects up until maybe the last gravitational wave cycle, which means the last half of an orbit. So it's at the really very end we are missing information. And you see the dynamical tidal model improves the agreement with numerical relativity, but at the moment we still have some uncertainty because we have only a low post-Newtonian order, and we have these effects only in the conservative sector, not yet in the dissipation.
Why is it that for black hole neutron star system there is practically no ring down?
Yes, I will get to that. Okay, so yeah, let me skip this one. And this is the final fate of neutron star black hole. That, as you saw, the most striking difference between a neutron star black hole and double black hole is that all of a sudden the neutron star black hole waveform completely ends and shuts off. And that happens whenever the neutron star gets so close to the black hole that the tidal force overcomes the self-gravity that's holding the material together, and the material is ripped apart. And then you can think of each mass element in that debris as radiating its own gravitational waves, and the net signal is the sum of all these mass element radiations. And once the material is sufficiently spread out, all the phases cancel and the net signal is zero. And this can be made quantitative by simply taking some single particle waveforms and superposing them so that initially these particles are on a sphere and then just letting them evolve. And you see this down here is supposed to illustrate the last blip in the waveform. The suppression is somewhat well reproduced.
So black hole accretion disk is not there, not important, or is it?
Here it doesn't have a big accretion disk. There's a little bit of an accretion disk formed, at least for some time, which, here maybe you see that the cancellation is not really perfect. Maybe that has an influence. We are still investigating this last tidal disruption part.
But you can put in accretion disk in the codes, or I'm just asking simple question. What's the status of that? Is that incorporated in the codes or not? Or okay.
Yeah.
So your team included everything.
Yeah, I mean in the numerical relativity code.
Okay.
In our model, not yet really. I mean we are just at the stage of further exploring that.
Mm-hmm.
So this difference is pronounced kind of when the masses are close, right? Because when the black hole is much larger than a neutron star,
it's like a point particle and just plunges in. Yes.
Yeah, so it's
yes. Yeah. But the point is, when the black hole has spin, then it again becomes more likely that it gets tidally disrupted. So, at least for some mass ratios, it's important to have this model of the tidal disruption. Because it could also occur in LIGO's sensitive frequency band, and then it's quite a dramatic signature if the waveform all of a sudden ends. And then, depending on which frequency that occurs at, that tells us again about the properties of the neutron star matter.
Maybe this is the same question, but how you model it as nuclear matter becomes a blob? How do we model that matter?
So here, so I use, so for in this EOB model, the effective, it's all, I don't have really a neutron star, I just have an effective particle with some quadrupole moment and so on.
So I understand the initial stage doesn't matter, but at that stage, I suppose it does.
Yeah, and then I evolve simply that effective one-body model up until where I say I estimate the tidal disruption occurs, and then I switch, instead of switching to a ring down of a perturbed black hole, I switch to a blob of particles.
Non-interacting particles? Or?
Yeah, but I mean at the moment we're not yet doing that, we just have a fit for this fall-off, but the hope is in the future we can make a more physical model.
I guess, why aren't you using the model with the tidal dissipation in the run-up to this?
Because before this disruption, the self-gravity is quite important. So the neutron star behaves like a coherent, I mean, you cannot really think of it as individual mass elements radiating their own gravitational waves. It's really one bulk neutron star is radiating. Does that make sense?
Okay, I guess I just would have thought in the black hole neutron star case, you would start with the model you had on the previous view graph.
Yeah.
Where you had tidal dissipation, changing the phases and all that.
Yes, and I still have that.
Oh, okay.
So what I showed here is, is up until, if you look in this window, in the waveforms, I just show the inspiral part. And then in the next slide, I show what happens after this inspiral part.
Okay, all right.
Do you have to assume, you have to at this point assume something about equation of state, right? So you're not exploring that any longer. but you assume something and then you compute.
Yeah, so we haven't explored yet how the blob of particle model depends on the density distribution of these initial disrupted material. Okay, any other questions? Okay, because now I want to talk about a completely different system, which is highly relativistic binaries. And those are sources for the future space-based detectors, not for LIGO. But they're...
Why you skipped neutron star? Like that's the next
thing?
Yeah, we talk about black hole, neutron star.
Yes, so neutron star, so this inspiral part is the same basically as I discussed, except, you have two objects, each has their tidal deformability, each has their resonance frequency. So that's the same. But at the moment, we don't have a good quality, let's say, we don't have, you see the numerical relativity waveform we use had a certain error associated with it. So for neutron star, currently, these errors are so large that they don't allow us to distinguish between different models. So even the adiabatic model would be consistent with that. So at the moment, we can explore these quantities better by comparing with neutron star black hole. Although, of course, mass ratio 2 and non-spinning is very unrealistic, but it helps us to develop the model. Okay. Okay. So, so these highly relativistic binaries are interesting because they occur in the centers of galaxies when there is a stellar mass black hole inspiraling into a much larger 10 to the 6 solar mass black hole, for example. And in this plot here, you see this gray line is the trajectory of the small object. So you see it's already quite interesting. And these inspirals will be observed for about a year in the detector band, and their orbital periods is of order minutes. So this will accumulate many, many cycles of waveform, and that will allow really high precision studies. So one can map out in detail the space-time geometry of the central object and know exactly if it's a black hole or not. And also it provides interesting information about galactic cores and black hole growth history and, of course, strong field gravity. Okay, so on short time scales, these inspirals, they look almost like test particle orbits. And these test particle orbits have the following features. So here is an orbit that is a bit less extreme than on the previous slide. But you see it's confined to a toroidal region between a minimum and maximum radius and a minimum and maximum inclination. And the shape of that region is determined by the constants of motion, which are the energy, the z component of angular momentum, and then a third constant, which is the Carter constant K. And there are three different...
Which is what? The third one is what?
The Carter constant. It's also related sort of to angular momentum. And there are three different frequencies of that motion. There's a rotational phi frequency, and then two fundamental librational frequencies, omega r and omega theta. And you see here is a plot of the frequencies versus the mean orbital radius. And the Newtonian limit is at large radii, and in that limit all the frequencies coincide. And then as you become more relativistic, I already discussed the frequency, the difference between the phi and radial frequency gives the periastron advance. And you see, as you get even more relativistic, these frequencies can become very different. So now, these inspirals are, of course, not test particle orbits, but it becomes important that the small mass also distorts the space-time. And the interaction of that small object with its own space-time distortion is what is known as the gravitational self-force. So it's similar to the self-force in electromagnetism. And that causes the orbits to slowly evolve. So just to give you some idea of this orbital evolution, so it has the following features. So normally in the test particle limit, the constants of motion are really constants, but then because of these gravitational self-force effects, they evolve. And this force can be expanded in powers of the mass ratio perturbatively. So there is a linear in mass ratio force and a quadratic in mass ratio force. And each of these pieces can be further decomposed in terms of a Fourier expansion, in terms of the fundamental periodicities of the system. So these Q's are some angle variables associated with the frequencies. Okay, and it's very difficult to compute these forcing functions. And at the moment, all we can compute is the leading order and mass ratio average piece of the force. So what kind of inspiral do we get with that? So here's sort of a cartoon version of the evolution of the constants versus time. And if we had the full solution, it would look something like the black line illustrated there. And using this zero force, we can get the adiabatic approximation, which is already pretty good in the sense that it makes only an order epsilon or a mass ratio error in the slope, which gets corrected by the second order average force. And it also neglects these small oscillations, which whose amplitude is also of order the mass ratio. So that's actually important that one can show this oscillatory piece of the force contributes at a higher order to the effect on the dynamics than the average piece. And of course, to compute templates, we need all of these three pieces of the force. But there's actually an effect that comes in that gives an even larger correction than, for example, the second order average force. And that is the occurrence of resonances. So resonances occur when the ratio of these frequencies becomes a ratio of small integers. Of course, you could take any integers and it would technically be a resonance, but only for small integers are the dynamics very different from an ergodic orbit, say. You see that illustrated here. For a low integer ratio resonant orbit, it looks quite different than a generic orbit. And here you see an illustration of where these resonances are. The bands are the location of the resonances, and a wider band means it's a lower integer ratio, so we expect them to have a more dramatic effect on the motion. And you see all of them are located in the strong field region. There are a few of them, and they are pretty isolated. And now an inspiral will pass through all of these resonances on its way to the event horizon. But now there's not always an effect. And so let me tell you what is the effect. So mathematically, it can be seen again by considering these equations of motion, where I've now written the phase of this oscillatory piece in more detail and expanded near the resonance. So remember, I told you before, normally this oscillatory piece contributes just a small correction to the dynamics computed from the average piece. But at a resonance, some of these normally oscillatory Fourier components have a stationary phase, and so they contribute order unity corrections to this 0-0 piece of the force. So then, well, maybe it's easier to see this picture here is now in evolution with the resonance. So I start out initially with two trajectories with a slight difference in initial conditions. And before the resonance, they're well approximated by the adiabatic approximation. But then at the resonance are large corrections. And then after the resonance, again, they're approximated well by an adiabatic approximation, but it's a different one than before. So it looks as if, since the resonance is so short on the inspiral timescale, it looks as if there is a kick in the constants of motion or a sudden jump across the resonance. And that jump depends on the initial conditions, and in particular the initial phase with which the system entered the resonance. And okay, the scaling of this jump with the mass ratio is only square root of the mass ratio, which is still small, but then the problem is this affects the frequencies, and after further inspiral that accumulates a phase correction. And that phase error is order square root of the big mass divided by the small mass, so it's much larger than 1. So this is a serious effect that has to be really taken into account. And currently, of course, this gives us the scaling with the mass ratio, but currently we cannot compute the net effect because we don't know these oscillatory forces. So to get an estimate, we could at least compute these forces in the post-Newtonian limit and then use them in an evolution to get an inspiral and get a net size of the resonance effect estimated under certain approximations. So here you see the result of this evolution, where in the upper panel is the constants of motion rescaled to their value at resonance and also with the square root of the mass ratio scaled out. And down here is the phase difference to the adiabatic approximation. And you see clearly at resonance the kicks in the constants of motion, and correspondingly a phase error starts to accumulate. And that could be of order tens of cycles. And so that's, of course, very interesting, but also it means more work for us because we have to take this into account. And also if there are multiple resonances, the dependence on the initial conditions might get quite complicated. Also, this phase correction is different than other kinds of phase corrections because there are these sudden jumps in the frequencies. So now to summarize, well, you heard recently that LIGO has initiated gravitational wave astronomy, so now gravitational waves are available as a tool for probing black holes, neutron stars, and gravity itself, and for making unexpected discoveries. And for one of the key sources are binary inspirals, and for those systems we need accurate models in order to extract all the information contained in the signals. And I discussed some recent progress on building such models. So I mentioned first the spin effects in comparable mass black hole binaries and how we use an effective one-body model to compute complete waveforms. I also mentioned interesting tidal effects that depend on the properties of neutron star matter. And I also discussed some interesting features of highly relativistic inspirals. And so as the outlook, over the next few years, starting with the next observing run this summer, many more detections are expected to come. In fact, one of the interesting outcomes of this first stretch of LIGO data was that the event rate for black hole mergers is at the very high end than what was previously thought. And so for extracting the maximum information from the signals, we need to improve current models, especially the modeling of matter effects in neutron star binaries. And this can only be done by also comparing with numerical relativity simulations to make sure the models are robust. And we have to include more realistic physics. And also, I didn't talk so much about this, but these neutron star mergers or tidal disruptions are also key sources of electromagnetic signatures because of all that nuclear material flowing around. So one could learn a lot more by combining electromagnetic and gravitational wave observations. And also for highly relativistic binaries, which is sort of more a long-term project, a lot needs to be done even in the absence of resonances and of course also including the resonances. Okay, so that was it, and thank you for
More questions?
So for neutron star mergers, is it typically expected that black hole will follow there, or?
yes, so it's probably, it really depends on many things in the system, but I think it's expected they will form sort of a hypermassive neutron star for some time, which is highly unstable, and then it collapses into a black hole. Yeah.
And what is the smallest mass black hole which one can get from that? Can it get much smaller than from usual supernovas?
Oh, I don't know. Yeah. I also don't know what you can get from supernova in terms of black hole. I guess you expect larger than the maximum neutron star mass. So.
Yeah. So the question: can one get smaller black hole mass from in this process?
I don't know. Yeah.
So it seems that you're saying that the case of neutron star cannot be simulated very accurately, right?
At the moment, yes.
So what are people using for the waveforms in those cases? Are using EOV or what is LIGO using?
So currently, since no neutron stars have been detected yet, they just have the detection template bank, and for that it's enough to use point particles because the tidal effects and other matter effects are so small. So they can just use the EOB waveforms or post-Newtonian waveforms to detect the binaries. And then once they're detected, one can think about what to do in this case. And the merger of neutron stars is anyway outside LIGO's currently most sensitive frequency band. So for neutron star, at the moment we have to focus on getting the inspiral models good. Whereas for the tidal disruption, that could occur inside LIGO's most sensitive band.
Can I ask you a somewhat strange question?
Yeah.
So let's say we're not talking about quantum computers, but within conventional computers that we have and then Moore's law.
Yeah.
So when do you expect that numerical GR would do everything that you want to do in a reasonable time frame for the experiment, and you won't need to know. Is there a time scale like that, or
no? It's simply impossible because as you move away from this corner of the parameter space and you go to larger orbital separation, it takes longer for an orbit. It takes longer to inspiral, so you have to simulate over such long times that it's computationally, even in 10 years from now, it's impossible to get. Say for neutron stars, you might have 1,000 cycles of waveform. It's not possible to have everything numerical relativity.
Okay.
At least not. Maybe you can do one case just to say you did it, but not for the entire template bank. And also for going to different mass ratios, that introduces many problems because they always have to resolve all the different scales. The black hole size is proportional to its mass, so if there's a small black hole and a large one, and then the inspiral time, it's very difficult.
Okay.
What do you learn from? I mean, you get something like this lambda parameter from if you measured one of these neutron star black hole inspirals. Like you get some estimate of its deformability.
Yeah.
What does that tell you about? I don't even want to express it as the equation of state, but what does it tell you about like nuclear forces when you know that? Like when you have one or two numbers about the neutron star.
Yeah, so, I mean, it would tell you, as you said, about the equation of state. That's what it's most sensitive to, not the microphysical details.
Right, yeah, but, so I guess I'm just wondering, like, what, I don't know that field particularly well, so I'm just wondering, what are people arguing about right now with regard to the equation of state of neutron stars? Like what, like, is there a particular question it would resolve, or?
People are, so, for example, these models that involve, so there are several uncertainties in the current models, which are, first of all, the composition of this matter at the very high density. So the main uncertainty is above maybe 2 times nuclear density in the cores. And
so meaning literally exactly what mix of particles is it?
Yeah, what mix of particles, and then also what are their 3 body forces or interaction potentials, because for some of these hyperons you might measure the masses in accelerators, but you don't know anything about their interaction potentials, which is very important for the neutron stars.
Just continuing along, Mike's excellent question, how about this quark-gluon dense state? Some people argue might be in cores of some of the neutron stars.
Yes.
So is that something that one could probe?
Yes, I mean, so the nice thing about now this dynamical tidal model that we have is which seems to be important, and so that it's not only the deformability parameter, but also this fundamental mode frequency that might be measured. So maybe.
Okay, so then you want to go.
Yeah, so maybe, probably they give similar information, but maybe not. I mean, that hasn't been explored yet, to go back from these gravitational wave observables to the fundamental properties. And also, because maybe there might be a better parameterization. Maybe it's better to parameterize in terms of some neutron star quantities instead of the deformability and frequency. But at the moment, if you have a model for some deconfined quark matter in the interior, you just have to compute the deformability parameter and the frequency and see if it's consistent.